So we are going to talk about gas laws today. So there are three main gas laws, and I'll state each one of those, and then we'll go through the problems. So the first one is Boyle's law, right here. Boyle's law states that the volume of a given amount of gas held in a container at a constant temperature will vary inversely to the pressure, which means as the pressure goes up, the volume will go down. So again, pressure goes up, volume goes down, and vice versa for that. The second is Charles' law. Charles' law states something a little bit different. It states that the volume of a given mass of gas is directly proportional to Kelvin temperature at a constant pressure. So that means as the volume goes up, the temperature goes up. And as the volume goes down, the temperature goes down. Charles' law, remember we have that Kelvin. Celsius doesn't work, so we need to make sure we always convert to the SI unit. And then the last one is our guy Luccac's law. With his law, he states that the pressure of a given mass of gas varies directly with the Kelvin temperature when the volume remains constant. So that means, again, as the pressure goes up, the temperature goes up. As the pressure goes down, the temperature goes down. So let's look at what some of these look like and how we determine which one we're using. So I did not state which gas law is which, so we're going to make sure that we do that when we go through the problem. So it says the volume of gas at a pressure of 99 kPa is 300 milliliters. If the pressure increases to 188 kPa, what would the new volume be? So we have a couple indicators right here that we can figure out which law we have. One, we have a P1 of 99 kPa and a P2 of 188 kPa. If we start looking over here, we have two options, Boyle's or Luccac's, and then we want to go to our last thing that it gives us, and that is a volume of 300 milliliters, asking us what our volume 2 would be. So with that, now that we have this, we can now look at a few different things. One, we have pressure and volume. That's going to be a Boyle's law. We have to look at what they're giving us, and then we can go from there. Well, Boyle's law is an indirect relationship, so we take our 99 kPa times 300 milliliters, set that equal to 188 kPa times x. And when we solve for x is equal to 158 milliliters. Because milliliters and liters are proportional to each other, we can just leave those as is, and we do not have to convert back and forth unless it specifically asks you. However, if one is in milliliters and the other is in liters, then you're going to have to convert because you can't have them in a relationship separate from each other. Let's try another one. We have the pressure of a sample of helium in a 1 liter container is 0.98 atms. What is the new pressure of that container? Okay, so again, pressure, volume, Boyle's law, P1 times V1 is equal to P2 times V2. So our P1 is 1 liter. Our P1 would be 90.988 atms. Our volume is 1 liter. Our P2 is an unknown, and our volume 2 is 2 liters. And so then we would just solve for x, and x is equal to 0.494 atm. Again, we're just making sure that we look for the problem and which of these that we have. Okay, so this says it has a gas at temperature. So right now we have a temperature, so now we know it's either going to be a Charles law or Luccac's law right off the bat. And then it has a volume. In degrees Celsius, what is the volume if it increases to 1.8 liters? Okay, so we have our V1 is equal to our 0.67 liters, and our V2 is equal to 1.12 liters, and we have a temperature. Since we're dealing with volume and temperature, we have to remember that we are in Charles' law. Now, we said that it was in Kelvin, so we have to convert this to Kelvin by adding 273, and so you have to convert, otherwise you will not get the right answer, just to let you know. And we get 362 K. So this is a proportion problem. These are proportional, so our V1 is 67 over our T1, 362, is set equal to our V2, 1.12 liters over X. And so when we solve for Charles' law, you'll get an X of 605 Kelvin, but they wanted our temperature to be in Celsius. So in order to do that, we have to subtract 273. When we subtract 273, we get 332 degrees Celsius, and this would be our answer. So we always have to make sure that we are in Kelvin for the following problems. And so if we would have our temperature, so this one is degrees, giving us a temperature. The Celsius temperature of a 3-liter sample of gas is lowered from 80 to 30. What would the resulting volume be? Again, temperature and volume are the two big indicators here. That means we're dealing with Charles' law again. So in this case, our V1 is going to be a 3-liter sample. Our T1, however, we don't have, because we have to convert that. So we are going to take our 80 degrees, notice I'm putting parentheses around this, plus our 273. You can do that separately if you would like. It doesn't really matter. This is going to be 353 if we add those together. Set that equal to, we're solving for that new volume, and our temperature was lowered to 30 degrees plus 273. This, again, in parentheses, would give us 303 Kelvin. And so some of you are probably wondering why. Well, we could just probably put it in and get the same answer, right? So when we solve for X using our 353 and our 303, our liters, our X liters is 2.58 liters, which is the correct answer. If you leave it at 80 and 30, you get a number like 1.5 or something like that. They're not proportional to the SI units. So whenever we start solving for these, we have to make sure that our SI units are proportional to one another. And if we don't convert to Kelvin, they're not proportional. And so they do not have that direct relationship, and therefore you will not get the right answer. Okay, so in this problem, it says a gas is sealed in a container at a pressure of 125 kPa at a temperature of 30. The container will increase to 201 kPa. What is the new temperature? So again, we're dealing with temperature and pressure, and now we're here into this guy, Luccac. So let's start looking at what we have here. So we have our pressure. So our P1 is going to be 125 kPa. They have our P2 at 201 kPa. We have a temperature of 30 degrees, which we're going to add 273 to get our new temperature in Kelvin. And we are looking for our second temp. Now, they didn't specify if the new temperature had to be in Kelvin or in Celsius, so we do not necessarily have to change it. Both answers would be considered correct as long as you have them. So let's start setting this up. We have 125 kPa over our 303 Kelvin is set equal to our 201 kPa over X. And so we solve for this. X is equal to 487 Kelvin, which would be a correct answer. If we subtract 273 from it, you would also get a temperature of 214 degrees Celsius. If it doesn't specify in Kelvin or Celsius, I prefer you just to leave it in Kelvin, but you could do it in Celsius too. One last problem. An automobile has a tire pressure of 1.88 atm at 25 degrees Celsius. That's about room temperature, by the way, 78 degrees. What is the pressure if it warms up to 37 degrees? Ooh, a hot day. So again, we're using that Gay-Lussac's law. We have our 1.88 atm. Notice ATMs are much smaller than kPa, and that is completely fine. Both are SI units. And we have our T1 and our T2. Again, converting our 25 plus our 273. We are going to get 298 Kelvin. And for our T2, 37 plus 273, we get 310 Kelvin. So we're going to set these up to each other. 1.88 atm over 298 Kelvin is equal to X over 310 Kelvin. We solve for X and we get 1.96 atm. And so that is our gas laws. Just remember that they have relationships, and when we're looking for those problems, what are they giving us? Are they giving us pressure and volume, which have an inverse relationship? Or are they giving us volume and temperature, which have a direct, or pressure and temperature? Just make sure that we look at the variables of which they're giving us, and then we can solve for the missing component.